morning, everybody. Welcome to the last week of classes, which is exciting. We've made it this far. Good morning, Joey. And everybody else who's here. Yeah, another Monday. I'm actually prepared for lecture today. We're gonna solve one system of equations using like every method we've learned. Good morning, JR. Good morning, Joey. The programming project was graded super fast. Chinmay was the TA that was assigned to my sections, G and H, and he graded them so fast. I had a student email me about their project grade, and I was like, wait, what? And I totally realized that they weren't released, or that they were released to you guys so you could see them. And I looked and I was like, wow, they really are graded fast. So to everybody who on Wednesday was saying, I wish I knew what my programming project grade was, congratulations. The grades weren't bad. They were pretty good. Yeah, I was impressed. Also, pretty crazy. Yeah, so I sent my final email to you guys on Friday, outlining what this week will look like. So you guys have a final homework due, and that's about it. I encourage you to just get it done as soon as possible, if you haven't already. For some odd reason, we're giving you guys an incentive to do the course evaluations. Yeah. So, do the course evaluations. If 75% of you guys participate, then you get an extra bump in your grade. Which this class is not curved. So 1% to everybody is really, like the way I phrased it in the email. Good morning, JC. The way I phrase it in the email is you get a 1% bump, because it doesn't matter if everybody gets a 1% bump, because the class isn't curved. So make sure you do your course evaluation so that you can get your 1% bump, which can make a difference at the end of the semester. It gives you a little bit of wiggle room on the final, given the fact that the final is 30% of your grade. It's a decent chunk. So 1% can make a difference. Right now, section G has a 48% response rate. So 29 out of 60 students have filled out the course evaluations. So go ahead and go bug the other 31 people who haven't filled it out. Because hopefully at least 50% of those will respond, and then you'll be at your 75%. If you guys want, I can keep you appraised on that percentage. Yeah. So go fill out your course evaluation, because you get an extra 1% on your final grade. Which, to be honest, that's like, oh, weird. Have you put on special spam filters to like filter out every junk email that you get from UB? You guys probably get so many emails. I mean, I get emails, but you guys probably get way more than me. I'm not gonna lie. All of those seminar emails and everything. So anyway, so you guys had a 48%, which is actually pretty good. I mean, it's way higher than it was in the previous, like, let's see, last spring, the response rate was like a 12%. The year before that was like a 35%. Nope, that's a different class. The year before that was at 28%. The year before that was 30%. But this is the first time that we're providing incentive. I mean, I care about the course evaluation. I do. I really want to hear your guys' feedback. I really appreciate it. So please give feedback. You know, JR, you'd be surprised at how many students don't, like, you get, like, this wide range. You get this set of students that they're students who do everything they're supposed to do, and for some obscure reason, course evaluations are on that list of things they need to check off. But they don't really give responses, and then you get that group of students who are like, this class was terrible, I need to respond, someone needs to see this. So it's a very wide range. Okay, moral of the story is fill it out because you'll get an extra 1%. Let's go ahead and start. Okay, so today, like I said, I am going to just go through solving the system of equations using every method that we've talked about. If you want a little review of everything we've talked about for linear algebra, because the final exam is going to be on linear algebra. We didn't include any MATLAB stuff. You don't need to have MATLAB stuff. So it's linear algebra. So we started out with vector algebra. Some things to focus on with vector algebra: make sure you know how to do a dot product, make sure you know how to take the norm of a vector, find a unit vector, the corresponding unit vector. You find the angle between two vectors, orthogonal vectors, and a linear combination. So I put those equations over here. I updated the notes document as well. But here's the equation for dot product, here's the equation for a norm, here's the equation for unit vector, angle between two vectors. And when we're talking about orthogonal vectors, this should be the one that comes into mind, where the dot product between the two of them is 0, comes from this equation, where cosine of 90 degrees equals 0. So therefore, u dot v would equal to 0. So when you think orthogonal vectors, think dot product between them is 0. And then here's my equation for linear combination. Project E. Yes, if you have questions on the project, please email me so I can go through those. You can use MATLAB for this exam. You can use MATLAB to check your answers. That is completely fine. You're allowed to have open notes, whatever you want to have access to. Google, steer away from Google for this exam. Really, you'll just need your notes. And you can check your work with MATLAB. Handwritten notes too, that's fine as well. Yeah, open note, open book, open UB Learns. Check your work with MATLAB. We will go over, so practice problems. All right, this one's actually really a practice exam. It's not really a practice problem, it's a practice exam. It will be released this afternoon, so I think at like noon or 12:30 or 1 o'clock. On UB Learns, there will be an additional folder in the week-by-week material called Final Exam. You'll find a link to the to a practice exam that shows you what kinds of problems are going to be on the exam. You'll notice that it's not just going to be straight up, here's a system of equations, do this. It's going to be, here's a system of equations, there's a variable missing, or there's a number missing. You need to solve for that number depending on a different situation. So we will go over the practice exam on Wednesday, and I will go through all of those problems. But you'll have a general idea about what the types of problems you'll have. And then, yes, so you can use MATLAB if you want. You do not have to, and in fact, do not get caught up with overly being obsessed with getting the right answer, because once again, you have 2 hours to do everything, do the exam and submit your work. So you don't want to get caught up in, oh, I didn't get that one exactly right, if you don't have time. Okay, so these are your equations that you want to use for the week A material. In week B, we got into Gauss elimination and Gauss-Jordan elimination, homework 10. This was the worst homework because it takes forever to do specifically finding the inverse. You do not have to do that on your exam. I'm just going to tell you right now, you do not need to find the inverse using Gauss-Jordan elimination on your exam. You do need to, however, know how to get a matrix in REF and get into RREF. So Gauss elimination and Gauss-Jordan elimination. Then we had week C with determinants. finding our determinants, using those to finding all of our cofactors, finding all of our determinants. We use that to find our inverse, a much easier way to do it, and also solve with Cramer's rule. And then in week D, we got into matrix factorization. We did LU factorization, PLU factorization. On the exam, you do not have to do PLU factorization. So just LU factorization for the exam. I mean, they're similar. Just one requires row swapping and one doesn't. Okay, and then in week E, we did linear independence. So essentially figuring out how we can determine what type of system we have, if it is consistent or inconsistent, and determine the number of solutions. So if we have one solution, 0 solutions, or an infinite number of solutions, those are our 3 options. And then lastly, in week F, so literally one day last week and then the last day, last Wednesday, we did eigenvalues and eigenvectors, finding eigenvectors, and then writing out the diagonalization. Okay, so all of that fun stuff is stuff that you need to know for the exam, which if you've been doing your homework, then you've been practicing. And that's the best strategy you can have for putting this, for doing the final. Practicing, doing your homework. If you did not turn in a homework, still go back and practice with those. Shoot, I forgot to post the solutions. I will post the solutions today. But go back and do those homeworks that you missed because that's the best way to practice for the exam. Okay, so let's go ahead and solve this system of equations using all of these methods in bold. I solved it using the finding the inverse using Gauss elimination. Oh my goodness. It took me a long time to double check. I mean, a long time being relative. It took me longer than the other methods doing that one, so I will do that one last if we need to, and same thing with PLU factorization. I'd actually rather do that one than finding the inverse using Gauss-Jordan elimination. But we're going to use all these methods in bold. So here's my system. Here's my system of equations. I wrote it in the form of AX equals B. You guys should know how to do this. Row 1 comes from equation 1, row 2 comes from equation 2, row 3 comes from equation 3. It really doesn't matter the order in which these equations are entered in. We know that by now. The first column corresponds to the first unknown, the second column corresponds to the second unknown, the third column corresponds to the third unknown. So if these unknowns were out of order in my system of equations, I would still need to order them appropriately in my A matrix. And then X is filled with all of my unknowns, X1, X2, X3. Note this order here corresponds to this order here. That's it on purpose. And then my B vector is filled with all of my numbers, my constants from my right-hand side, from equation 1, equation 2, equation 3. So we've put together AX equals B plenty of times by now. And then here we have our augmented matrix. So our augmented matrix is based on the idea that it doesn't really matter what our unknowns are called. We could call it X1, X2, X3. We called them A, B, C. We could call them X, Y, Z. It doesn't really matter. All that matters is the numbers in A and B. And so this is my A side and this is my B side. Woo-hoo. Okay, so I want to solve this system of equations. Depending on what method I'm using, I might want it in the form of AX equals B, or in my augmented matrix. It really depends on whether or not I want A and B together or I want A and B separate. So our first method was Gauss elimination. So let me go ahead and copy. For Gauss elimination, the first thing we want to do is we want to write out our augmented matrix, which I've already done. But I only copied the middle. And then what we're going to do is we are going to apply row operations. So we have 3 row operations we can apply. We can swap rows, we can multiply a row by a constant, and we can replace a row by adding it to some multiple of another row. So I know by definition it's to some non-zero multiple of another row, but in LU factorization we kind of played around with, or we kind of modified that definition with. But ultimately, we want to do row operation 3. We want to do our elimination step. We want to get a 0 here, here, and here. So the first thing I want to do is I want to get zeros in my first column, because we should always start, if we want to do the least amount of mistakes, we typically start by putting zeros in our first column. So I'm going to do that by saying that row 2, I could do row swaps if I wanted. I tend to avoid them unless I know it would make my life easier. But I'm going to say row 2 equals, come on, pen. Row 2 equals row 3 times row 2. Oh, come on. Plus 7 times row 1. I can use whatever row operations I want for Gauss elimination. So if I do that, I multiply row 1 by 7, so I get 21, negative 49, 21, negative 49, and then row 2 by 3, so negative 21, negative 18, negative 9, negative 159. I chose a system that has bigger numbers, which was part of why Gauss, finding the inverse using Gauss elimination was so annoying. And in your exam, you will not have larger numbers, you will have smaller numbers to work with. But anyway, when I do this, row 1 doesn't change. Row 2 now changes. I get 0, negative 67, 12, and negative 208. So I just added these two together. And then for row 3, I'm going to say row 3 equals row 3 plus row 1. So I'm taking 3, negative 7, 3, negative 7, and then negative 3, 5, 7, and 49. So add these two together. I get 0, negative 2, 10, and 42. So I've got my zeros in my first column. Check. Joey, the best way for checking your work for mistakes. The best way to check your work for mistakes is to write out all of your work. I want to point out that on your final exam, you're going to be graded. So I wrote the rubric so that you're graded mostly on your process. So it's not as important about getting the final answer as it is to show that you know what you're supposed to be doing. So here, by writing these numbers out, I am showing that I am doing this row operation. I'm taking 3 times row 1, or 7 times row 1, and 3 times row 2. Checking your work is easier this way because you don't have as many things squished together, as many operations squished together. You can see, oh yeah, I did forget to carry that sign through. Another way, like sometimes for these problems, you just kind of have to go all the way through and then be like, ah, shoot, I got that wrong. And then you have to go back. Once again, though, you're not graded as much on the final answer as you are on your process. So if you do your process correctly, you're gonna get most of the points versus if you just kind of show, okay, I'm doing these 3 row operations and then you find your final answer. Yes, you can use your calculator on the exam. Okay, so I've got my zeros in column 1. Now I want my 0 here. So I ended up with this stupid 67 here. My toddler's at school, so I can say the word stupid. I've got my 0. I want to get my 0 here. So my last row operation is take row 3 equals 67, row 3 minus 2 times row 2. So if I multiply row 2 by negative 2, I get 0, 134, negative 24, 416. And then if I multiply this one by 67, I get 0, negative 134, 670, and 2814. So when I add these two together, I end up with row 1 doesn't change, row 2 doesn't change, and row 3 now becomes 0, 0, look at my page, 646, 3230. Like I said, you will be dealing with smaller numbers. Can't remember if there are any significant fractions. But you'll be doing with smaller numbers. You might get fractions with LU factorization. But at the end of the day, you should end up with numbers that divide out. So if I write my system of equations now, so I've got my lower triangle of zeros. So that's the first thing, or the second thing with Gauss elimination. You want to write an augmented matrix. You convert it into REF. Use row operations to get REF, where you have your lower triangle of zeros. And then you write your system of equations that result. So here, I can see that 646 x3 equals 3230. When I divide this out, I find out that x3 nicely is 5. So now I'm going to plug that into this equation. So I get negative 67 x2 plus 12 times x3, which is 5, equals negative 208. And if I solve for x2, I see that x2 equals 4. So now I've got x2, I have x3, I can go ahead and plug those into my first equation, which tells me that 3x1 minus 7x2, which is 4, plus 3 times 5, which is x3, equals negative 7. And here x1 equals 2. So once again, you're graded on the process. So showing this and then jumping straight to your answer is perfectly fine in showing your work. Over here, you are showing us that you know how to write your system of equations. You're showing that you know you plug in a 5 here and a 4 here. But the step from here to here is relatively basic algebra. And you can type that in your calculator. But jumping from here to here does not show us that you know what you're doing. That just shows us that you can type something into MATLAB. So make sure you're showing enough work to demonstrate that you know the process, because the process is what matters. Okay, so there we go. We just solved our system equations using Gauss elimination. Woohoo! We did it. Okay, that's Gauss elimination. Gauss-Jordan elimination is very similar. I still start with RREF, or with my augmented matrix. I still want to get my first column of zeros, which in order to do that, I do the same row operations I did up here, so I'm not going to show that work. I'm going to write them down though. R2 equals 3 row 2 plus 7 row 1. Row 3 equals row 3 plus row 1. When I do that, I end up with the same matrix I got here. And then I want to get my zeros in column 2. So I want a 0 here and a 0 here. So I'm going to say that row 1 equals, showing my work, 67 row 1 minus 7 row 2. So I multiply row 1 by 67. I end up with 201, negative 469, 201, negative 469. Multiply row 2 by 7, or negative 7, I get 0, 469, negative 84, and 1456. You do not have to stick with whole numbers. I prefer whole numbers. I find them easier for me to work with. They're also exact. You're not dealing with rounding. So you could choose different row operations. Joey, if you are asked to do Gauss-Jordan elimination and Gauss elimination, yes, you can just start where you picked off. That's not a problem. I'm just demonstrating both of these from start to finish, more or less. So that means once I do this row operation, once I add these together, I get 201. Where am I? There I am. 0, 117, and 987. That was a fun one to find. I wrote 989 down when I was making my solutions here. Took me a very long time to find out that I had multiplied something wrong. So once again, the best way to check your answers, to check your solutions, is writing out all these steps to say, oh, I did multiply that number incorrect. But once again, it's not, if you make a minor math error, it's not the end of the world. You're not going to lose all of your points. You get points based on the process, which is the most important. Row 2 doesn't change. And then row 3, in order to get my 0 here, I would do the same row operation I did up here. So row 3 equals 67 row 3 minus 2 times row 2. So if I do that, I get the same thing I got up there. 0, 0, 6, 46, 32, 30. Then, in order to make my life easier, I'm going to divide this row by 646. So I can just delete that for the sake of speed. You would show out the work. Okay, once I do that, I want to get my zeros here. Woohoo! So I can say row 1 equals row 1 minus 117, row 3. So I get 201, 0, 117, 987, and then 0, 0, negative 117, and negative 585. And then to get a 0 here, I would say row 3 equals row 3 minus 12. I would say row 2 equals row 2 minus 12, row 3. So I get 0, negative 67, 12, negative 208, 0, 0, 12, negative 12, and negative 60. And I end up with this. So given that my system, the answers are 2, 4, and 5, I know that RREF always ends up with this. And my solution ends up being on my B side. So if I know what my solution is, I know what my RREF should look like, which I'm almost there. My last step is to divide my first row by 201 and my second row by negative 67. And it turns out when I do that, I nicely get my solution. So there we go. Here's RREF. Get this side as close to identity as possible. And here's my solution. So it tells me x1 equals 2, x2 equals 4, and x3 equals 5. Are we allowed to divide a row by a constant to get the 1 in the identity just in the middle of our... Yes, you can do any valid, like here, you can do any valid row operations you want in any order you want. You can swap them anytime you want. You can divide them by a constant or multiply them by a constant whenever you want. You can add them together whenever you want. Some row operations are just more beneficial than others to do. Like, it wouldn't make sense necessarily for me to divide this one by 201 to get this 1 here yet, because I still need to get a 0 here, and I don't personally want to deal with fractions. But it does make sense to do that right here right away, because I know it's going to benefit me in the future. I don't have to deal with such large numbers. I can divide it out, and I can deal with smaller numbers. So you can do any row operations whenever you want, as long as they're valid. You just typically want to do them in an order that makes it more beneficial. Yes, not just, yes. So Gauss elimination, you want to get to Gauss elimination, you want to get to REF. You just want your lower triangle of zeros. For Gauss-Jordan elimination, you want to take it all the way to RREF, where you get your lower triangle of zeros, your upper triangle of zeros, and your 1s along the diagonal. And note, the two give me the same answers, which is what we expect is the same system. Woohoo! There we go. Like I said, the third method we've learned with Gauss-Jordan and Gauss elimination was finding the inverse, which you will not have to do on the exam, but just a little bit of review. I would put A here, put identity over on this side, and then I would do my row operations. It turns out I would literally do the same row operations I would need for Gauss elimination, or for Gauss-Jordan elimination. These same 6 row operations. Note, there's 6 row operations needed. 6 row operations needed for 6 zeros. And then some ones to divide as well. But I would do those same row operations until I end up with identity on this side, and then A inverse shows up on that side. The hard part about Gauss Jordan elimination is there's just so many more numbers to deal with. For some obscure reason, those additional 2 columns like make everything frustratingly even more annoying. So you do not need to find the inverse on the exam using Gauss Jordan elimination. The final exam is open notes, just like the midterm. Okay, so yay, that's a whole page of notes I don't need to look at anymore. Okay, so let's go ahead. That was week B material. Moving on to week C, like I said, we can find the inverse now using cofactors and using Cramer's rule. So let's go ahead and do that. So for inverse, using cofactors, because it's the easier way to do it. So this time though, I really don't care about the augmented matrix. I want it in AX equals B. So I'm gonna copy A down. And I will need B eventually. But right now, I only care about A, because I want to find the inverse of A. So to find the inverse of A, I'm using my equation A inverse equals 1 over the determinant of A times A adjoint. Which I know I need to find the determinant of A. But I'm going to put a pause on that right now, because finding A adjoint, I need to find all of my cofactors. So the first thing I'm going to do is find all of my cofactors. And then I can use my cofactors to also find the determinant of A. But first I want to find all my cofactors. So C11. In order to find your cofactors, you're going to, so I'm at 1, 1. So I'm here. I'm finding the cofactor for this number. I'm going to remove the row and the column, and then find the determinant of that remaining matrix. And then I also need to apply my grid. So for this 1, 1 number, it's a positive. And then I move on to my next cofactor. C1, 2. Remove the row, remove the column. Find the determinant of the remaining numbers. And then apply my grid, which for this number is a negative. And then I keep moving on. Remove the row and the column for C1, 3. Find the determinant, and then apply my grid, which is a positive. You may see, so there, yes, you may see a 4x4, but it will not be, it will make it, if you see a matrix bigger than a 3x3 on the exam, don't be concerned, because it's probably going to be filled with a bunch of zeros that makes your life easier. So if you have a matrix that's full of zeros and you're finding the determinant, make sure you're checking to see first if it's a triangle matrix or a special kind of matrix that makes it easier to find the determinant. Okay, and then I keep going. So for C2, 1, I get -7, 5, 3, 7. That's a minus. C2, 2. My remaining numbers are 3, 3, -3, 7, and it's a plus. C2, 3. I like to write it all out just because then I can find all of my determinants, just because then I'm in the zone. I'm like, yeah, let's go. Let's find all these numbers, and then I can do my calculations. So my remaining numbers is -3, -7, -3, and 5, and that's a minus. And then for my last set, 3, 1, it's a plus. -7, -6, 3, -3. Also, if you don't do all these right away, then you can kind of make sure you're picking out the patterns. Not shoved to answer your question. No, the cofactors are just the determinants with the sign changed. If you are doing cofactor expansion, yes, you would need the value from your matrix inside. So you need to make sure that you're identifying what you're trying to calculate. These are just my cofactors. So I just need the determinants. If I'm doing cofactor expansion, then I also want to multiply my determinants by the corresponding number inside my matrix. Okay, so when I do these calculations, I get negative 27. So these are just 2 by 2s. So you should write out that you're doing that operation, but I want to make sure we get through a lot. 64, 30, 6, 39, negative 12, and negative 67. So once again, Joey, going back to your question of how do you check your work, what's the best way to check your work? Literally write things out. So maybe not saying 6 times 7, maybe say negative 42 plus 15 equals. Here, negative 49 minus 9 with my minus. Here, negative 35 minus 18. Negative 49 minus 15 with a minus. 21 plus 9 with a plus. 15 minus 21 with a minus, etc. So showing all of your, being like, oh, and then going back to check your work and say, okay, I know this number was incorrect. Going back to be like, totally forgot to change the sign, or 3 times 3 isn't 18, it's only 9. So just make sure you're writing things out. Okay, so my adjoint matrix, so I got on my cofactors. I have on my cofactors. That's the first thing to do when you are finding the inverse using cofactor expansion. Or using cofactors. Okay, so I need to get my determinant, and I need to get my adjoint matrix. My determinant, I can use for cofactor expansion. Cofactor expansion, you can use any row, any column. I'm going to use row 1 just because that's the row I normally use. It's my default if there's no zeros. So for row 1, I'm going to take the number times its cofactor, which is negative 27, plus this number times its cofactor, which is 58, plus this number times its cofactor, which is negative 53. Keep in mind, the grid has already been applied in finding these cofactors. So just double check, make sure you know where your numbers are coming from and what you're trying to do. And this gives me, my determinant ends up being negative 646. Okay, so it's not 0. That's great. That's fine and dandy. Which means the inverse exists, which means a solution exists. So we know now that a solution exists. If a unique solution exists, that means your determinant isn't equal to 0. That means your inverse exists. That means your rows are linearly independent. All those fun things we learned in week E. So here's my determinant. Now I want to find my adjoint matrix. Which your adjoint matrix is the transpose of cofactors. So here's my cofactors. Let's pretend they're all in a matrix. So I'm going to transpose it. So these first 3 cofactors become my first column in my adjoint matrix. So negative 27, 58, negative 53. The second set of cofactors from row 2 becomes column 2. So 64, 30, and 6. And then this last set of cofactors from row 3 becomes column 3. So 39, negative 12, and negative 67. So there we go. I have my inverse. A inverse is 1 over negative 646 times this beauty of a matrix. Let's move it. Woo! I found A inverse. You can multiply it through. You don't have to. I don't want to end up with a bunch of small numbers. So I'm just going to keep it out. And anytime you have the inverse, you can use it to find your solution by just saying x equals A inverse times b. So I'm just going to multiply this by b. That is not b. That is my solution. -7, -53, 49. So once again, I can keep my fraction, my determinant out. And then I just show my multiplication. So -27 times -7 plus 64 times -53 plus 39 times 49. So dot product between this row, this column. And then I do that again, dot product between this row, this column, and then this row and this column. That's a lot of numbers. So I'm not going to write it out just for time's sake. So when I do this math and I divide it by this, I end up with my solution, 2, 4, 5, which is what I expect. Once again, the process matters. It's not enough that you just show this and then the solution. You can't, you can't not have this in there. You need to show us that you know the process, that you know what you're doing, that you know how to take the dot product between this and this, because that shows us that you know how to do matrix multiplication. So not if you're finding the solution, if your end goal is to find the solution to a system of equations, yes, this is your final step when you're finding the inverse. You would say x equals A inverse times b. And there you go. Okay, that is finding the inverse using all of our cofactors. The next one was Cramer's rule. Or Cramer's method, whatever. Cramer's way to find the solution. Cramer's rule, we need to find 4 determinants. We need to find the determinant of A. We already know it's -646. So I'll just use that from above. We know how to find the determinant of A. I also need to find the determinant of A1, of determinant of A2, and the determinant of A3. Determinant of A1 is where I take A and I replace the first column with B. B looked like this. And then the rest of A looked like this. So this column comes from B, these ones come from A. So to find this determinant, I'm going to use cofactor expansion along column 1. So cofactor expansion along column 1 is going to be -7 times the determinant of this. Plus this number times the cofactor of the remaining, the corresponding cofactor. So my grid has a minus here, so I put my minus there. Plus this number times its cofactor, which is the determinant of my remaining numbers. Wrong one. You can do that in multiple steps. You can do that in one step. When I do that, I end up with -1292. Which means right here, based on just these two determinants, I can figure out what x1 is. x1 equals -1292 over -646, or x1 equals 2. So you might be asked to find part of Cramer's rule, given the fact that you only need to find 2 determinants. But once again, showing the process. To find the determinant of A2, I take A and I replace the second column with B. So my second column comes from B. So this comes from A, this comes from B, this comes from A. And I find the determinant. You can find the determinant across any row or column. I used cofactor expansion along column 2. That's my grid sign. So I get -7 with a minus in front times the determinant of the remaining numbers. Plus -53 times the determinant of remaining numbers. Plus -49, or plus 49. So negative in front for my grid. When I do that, I end up with -2584. So now given the determinant of A and the determinant of A2, I can find x2. And x2 ends up being 4. And I would repeat for A3. My determinant of A3 ends up being -3230. So x3 ends up being 5. Woohoo! Note for each of these, it's x of k equals the determinant of AK over the determinant of A. So determinant of A1 over A gives you 2. Determinant of A2 over A gives you 4. Determinant of A3 over A gives you 5. Okay. 8 minutes. Our 6th method was LU factorization. So for LU factorization, I want my A matrix. And I'm going to apply the same 3 row operations every time. I'm going to say R1 equals R1 plus a multiple of R2 equals row 2 plus a multiple of row 1. R3 equals row 3 plus a multiple of row 1. And then R3 equals row 3 plus a multiple of R2. So that first one is going to be 7/3. Row 1. Now I am very much, there are 6 questions on the exam. Now I am very much restricted by my row operations. It's these 3 every time. I cannot change them. So my first one is row 2 equals row 2 plus 7/3 row 1. So this number over this number. And then row 3 equals row 3 plus 1 row 1. Showing your work, which is what you should do. But once I do those, I should end up with this. For the sake of time, I'm not going to show you the work. And my last row operation is row 3 equals row 3 plus -6/67 row 2. Literally this number over this number. But once again, I cannot change my row operation. It has to look exactly like that. I end up with 3, -7, 3, 0, -67/3, 4, and then 0, 0, 6, 94 over 67. So here's where you might run into some fun fractions. But once again, on your exam, you'll be dealing with smaller numbers. This ends up being U. And then L is composed of all of these numbers. So L21 is going to end up being -7/3. So you need to change the sign. L31 is -1, and then L32 is 67, or 667, so it's positive. So keep in mind, and I know I probably messed this up during lecture, keep in mind these L's are the ones that go inside of your L matrix. So you might be asked to find a specific L value. Make sure the sign matches, because these are opposite. Fun stuff. So we have L, we have U. If you want to check, you could say L times U equals A. That's one of those checks that you might look for in MATLAB. If you have time, you would type in your L matrix, you would type in your U matrix, and you would see, okay, yep, it matches A. Once you have L and U, then you want to solve your system of equations. So essentially, we're rewriting AX equals B in the form of LUX equals B. And then we break it up into two pieces. Ly equals B and UX equals Y. So first we have L. Y equals B, which was, if you don't remember, -7, -53, and 49. So this first equation tells me that y1 equals 7. This second equation tells me that -7/3 times 7 plus y2 equals -53. Or that y2 equals -208/3. I encourage you to keep it in fractions. So Sarah, just keep in mind that in your row operation and in L, they're opposites of each other. So if you're told that L32 equals 15, then your row operation looks like this. R3 equals row 3 minus 15 times row 2. So given your L value, you should be able to construct your row operation. Keep in mind that the sign is opposite. So if you're told that L32 equals -1, then your row operation is going to be R3 equals row 3 plus 1 times row 2. So just remember in the back of your mind what your row operation it looks like and what goes in your L matrix, that they're opposite signs. And then for this last equation, it tells me that -1 times 7 plus 667 times -208/3 plus y3 equals 49, or that y3 equals 3230/67. Once you know those values, you can solve your second one, ux equals y. So u looked like this. And then y looked like this. Once again, it's about your process, so even if you get your answers wrong, keep moving through the process. Then you can solve this system of equations. 694/67, x3 equals 3230/67, which tells you x3 nicely equals 5. Isn't that nice and convenient? You can plug that into this one, which tells you that -67/3 x2 plus 4 times 5 equals -208/3, which tells you x2 equals 4. Also nice and convenient. And then plugging all of that into this last equation, you get 3 times x1 minus 7 times 4 plus 3 times 5 equals 7, or x1 equals 2. And there you go. It all matches. Okay, so we just went through a lot. We went through all of our methods. Think about how much you've learned in the last 5 weeks, really. Think about the first time we went over row operations and you're like, what is she doing? And now you're like, okay, that makes sense. That shows the math. Okay, yep, I know what I would do. Same thing for Gauss elimination, Gauss-Jordan elimination. Finding the inverse using cofactors. There's lots of little pieces with cofactors, but they're easier. It's just making sure you know where all the numbers come from. Kramer's rule, it's just a bunch of determinants. Once again, if you have a matrix that's bigger than a 3x3 and you're asked to find the determinant or something, make sure you're checking to see if it's a special kind of matrix. The determinant of a triangle matrix, you just multiply the elements along the diagonal. If you're asked to find the determinant using your determinant properties, once again, it should match up with your determinant properties. It should be relatively straightforward. With LU factorization, it's these same 3 row operations every time. If it's more comfortable for you as well, you could also do the idea where we know what L looks like. And what U looks like. And use it that way where you do the multiplication. You'll have your notes. So if you want to do that matchup instead, that's completely fine. Keep in mind, once again, your row operations and your L value, they have an opposite sign. Okay. JR, the final grade is just like our homework. Yeah, more or less. More or less. I did mention in the grading rubric for the final that more emphasis is placed on the process. So once again, follow the process. Even if you know something is wrong, don't worry about it. You can like note and say, I know it's wrong, but I'm still following the process. So that's not wrong, but you can still follow the process. Okay, with that, I'm gonna stop. On Wednesday, we are going to go over the practice problems that are gonna be posted later today. So before Wednesday, I encourage you to finish up your last homework and look over those practice problems. The solutions to the practice problems will be posted on Thursday morning, but they will all be there on UB Learns. And with that, I'm going to be done yawning. I'm going to jump over to office hours, and I will see all y'all on Wednesday for our last lecture. We're getting there. Okay.